Good morning, everyone. My name is Taylor. I will be moderating today. I'd like to introduce Piotr, who will be our speaker and sharing with us. We'll have some time for questions at the end. We just ask that you hold questions until then. All right, you ready?
Good morning, and welcome to this session on integrating FHIR with analytics pipeline. My name is Piotr Szul. I'm a senior software engineer at CSIRO, which is Australia National Research Agency. I work for FHIR Technology and Tooling team. Oh, we don't see the slides. Excuse me, we don't have the slides. Oh, it is not on the main screen. Yeah, that's better. Okay, so I work in FHIR Technology and Tooling team at Australia FHIR Research Center. I have been working in FHIR for about 3 years and mostly developing tools for FHIR-based analytics. And before that, I've been working many years developing tools for analyzing all kinds of research data. But I don't have much experience presenting like this, so I'm probably going to be talking very fast. And if I'm talking too fast, just let me know, wave to me, say slow down, because this might be just too fast for me. Okay, so today we're going to talk about how to build simple automated pipelines for FHIR analytics using open source software such as Apache Spark and Pathling. Also how to use FHIRPath and SQL to transfer complex FHIR data into simpler use case-centric tabular views, and how to tackle some of the complexity working with FHIR extensions, terminology, and questionnaires. Session has 2 parts. Part 1 is about the FHIR analytics pipeline, and here is, if you want, a GitHub repository with the code that we'll be going through. And we'll essentially introduce the use case, then talk a little bit about the solution, and then go to the code and look at some code. And then in part 2, we'll do the same thing for the small complex topics about using FHIR. So the scenario for today is what we call self-service analytics. We have some data analysts that have some knowledge of SQL and maybe tools like Power BI or Tableau, and we want them to be able to leverage FHIR in their analytics. And specifically, we'll be thinking about doing some form of COVID-19 management. We would like them to be able to define some customizable risk score for COVID, and then be able to answer the questions such as how many people with different risk score in different locations, or which areas are the most exposed to COVID-19, essentially simplifying, be able to produce something like this, some kind of heat maps that show us what are the risky areas for COVID-19. And in order to do this, we have to address 2 challenges. The first one is that our business analysts and our tools ideally would like to connect to an SQL database. And at the moment, our data are in a FHIR server, so that's not working. And then the other is that the FHIR model is very complex. It has many integrated resources, very nested. So even we can possibly put the data into an SQL database, it may be too complex for the data analyst to work with. So our pipeline needs to do 2 things. Firstly, move the data from FHIR server into SQL database, and then also hopefully simplify the data in such a way that it has only relevant information and the data analyst can work with it. And we'll call this simplified data our use case-centric view on the data. In our case, we will be using data such as some patient data, so maybe postal code, birth date, and then whether they have been immunized for COVID-19, and also some of the factors that are known to be contributing to severity of COVID-19 disease, so maybe having a heart disease or being obese. So these are the things that we like to include our use case-centric view. And then we want to also have some flexibility, so we'd like this solution to be somewhat extensible, so that we can also try to produce other use case-centric views if we need to. So one way to design such a batch pipeline, we try to go through this way here. So we start from the end. We want to have this use case-centric view and SQL database, and one way to do this is to create a replica of our FHIR data in an SQL-enabled warehouse or a database. Because once we have this, we can try to use SQL, maybe enrich with some terminology functions to extract data that we need to create this use case-centric view using SQL. And one of the solutions we can use is Apache Spark Data Lake, which is essentially a warehousing solution optimized for large-scale SQL queries based on Delta format. That's a bit here. So how do we put the data into this Delta Lake? Well, we can start from our FHIR server, use the FHIR Export API to export resources that we need from the FHIR server into a staging area in file system, and then use something to encode our data from JSON to this Delta format and then load it into the Delta Lake, essentially creating a replica. And the Delta format is an extension of Parquet format, which allows for updating of data. So we can technically do this many times all over again and merge data with existing data in Delta Lake, creating the updatable replica of the data in the Delta Lake. And then when we hit dash, we can use SQL to create our simple view in our SQL database. Okay, how does FHIR look in SQL? This is not yet very standardized, but there is work called SQL and FHIR that tries to define how we map FHIR data into SQL. And some things are fairly simple and intuitive. So for example, simple primitive elements like active can be mapped to simple fields in the SQL schema. Elements with multiple cardinality can map to arrays. Complex type can map into structures. Other things like choices and extensions are a bit more complex, and we'll talk about some of them later. But essentially, there is a way to represent FHIR data in SQL tables. The implementation will be using technologies shown on this slide here. Most prominent Apache Spark, PySQL, and also Pathling, where I talk about in a moment. And this demonstration is going to be implemented on Databricks platform in form of notebooks. And this is primarily because it's fairly to demonstrate how the pipeline works and demonstrate the code. But the same solution can be deployed pretty much on any Apache Spark enabled platform that includes most of the common cloud platforms such as AWS, Google Cloud, and Azure. So the code is pretty portable. And Pathling is a tool we're developing at Australian FHIR Research Center. It's a set of open source tools that facilitates use of FHIR and emerging data analytics. It's built on Apache Spark for scalability. We have libraries for Python, Scala, and also FHIR's API. And the features that are relevant for this pipeline are the fact that we can encode FHIR data from JSON to Delta tables. We can extract tabular views using FHIRPath expression, also adding support for terminology functions in SQL and FHIRPath. So that's what we need for the pipeline, essentially. Okay, so now we'll go to the code. This is the pipeline. I will keep this slide for reference so that we know where we are in the implementation. So, okay, so the first step again is exporting the data from the FHIR server to an staging area. And we have a notebook here, hopefully somewhere. Not this one. This one. Okay, so what this does is we have a notebook that will go to a FHIR server that has the bulk export by enable, and then export set of resources that we find here, and then download them into a staging area in our local file system or cloud storage. And there's a little bit of Databricks magic code here, but all this does is kind of enable us to define parameters for the notebooks that we can later put them together into a workflow. But at the moment, we're going to use default values. So we're going to connect to one of the demo servers from the FHIR bulk export API. We're going to download resources of patient, condition, provisionization, and then download them to a staging location in our cloud storage for Databricks. And the code itself is very simple. So we use Python to essentially initiate the bulk export request. Then we wait for the server to complete the export and then download the final response for the export. And you can see that there are some URLs to some of the resources that are being exported. And then part two on the notebook is we go through these resources that the server exported and just download them back to our staging area in our cloud storage. And as you can see, as we expect, actually, we now have all these resources downloaded here that represent the data from the FHIR server. And you can also go to Databricks Explorer and actually verify that we have these things locally downloaded in our, sorry, it's not this one again. I think it's this one. Yeah, so we have the resources, the JSON files for the resources. And that essentially concludes step one of the pipeline, where now we have the data exported from the FHIR server to a staging area. So the second step is encoding them into Delta and merging Delta Lake. So that's step two of the pipeline. So this time we are starting with a staging area and then define the name of the data lake schema, which would load the data to. And this is the first time we're actually using pathling. So to use pathling, we need to first initialize it, creating what is called pathling context, providing Spark session as an argument. And then you use pathling read ndjson function, providing the URL to actually encode all the resources that were in the staging area into Spark data frames. So what we are creating essentially is what we call a pathling data source, which is conceptually a map that maps resources into their corresponding data frames. So for example, we can verify that after running this, we actually have resources for each of the resources we exported, and then we have some data for them in this data source. And then we can use another function of pathling called write tables, which now takes all these data frames that are in the data source and then writes them back into a schema in the data lake, creating a table for each of the resources. So that's what we do here. And at the end, actually, we are having now all these tables, condition, station, observation, with our DevDays FHIR schema. And how this look in practice is we can go to Data Explorer and kind of have a look at the schemas. And we have this database here, or the schema, and then we have actually tables for the resources, and we can also look at the data and see that there are some actual data, hopefully, there. It will take some time, but it probably will show there. Yeah, that's the data. So this is the representation of our FHIR data, raw FHIR data in the SQL schema in the data lake. And that essentially concludes part 2 of the pipeline. So now we have this replica of our data in SQL in this data lake. So now we would like to form our view, extract what we need, the information that we need, and kind of create this simplified view. But before we look at the third step, let's have a look at how we can actually use SQL or FHIRPath to extract information from this rich FHIR data model. So let me go to... this notebook here. So this notebook demonstrates how we can use SQL, or more precisely Spark SQL, to extract the information that we need for our risk-centric view from this whole rich FHIR data model. And we actually want to create a view that has information for, the one that we saw on the slide, so postal code, and then the vaccination status, and then the factors that may contribute to COVID-19 risk. And the first thing we do actually is again creating the pathing context, and this is because it will allow us to use terminology user-defined functions. So we have the function member of, which we can use to test for coding membership in a value set, and function named subsumes, which tests between subsumption action between 2 different codings. And it's going to be useful to find some things. So extracting basic attributes is fairly simple. So we can easily get address, birthday. There is a syntax that allows us to address arrays and unnest different structures of postal code. So that is fairly easy. Then we can try to use these UDFs, for example, subsums, to identify all the conditions that are, for example, heart diseases. And to do this, we essentially identify all the conditions for each code, subsumed by the SNOMED CT concept for heart disease. So that's what we can identify the conditions that are heart diseases conditions. Similarly, we can use the same approach to identify conditions that are chronic kidney diseases, but in this case, I use other than SQL Spark Python data frame API, which allows us to use some helper functions that pathing provides to define, for example, SNOMED codings without needing to specify everything there. Then we can also use similar approach to identify all observations that are of BMI, so body mass index type. And then we can try to look for this that have certain value. The complexity here is that the value of the observation is a quantity which has a unit. So it's maybe a bit hard to compare these things, but Pathling provides an extra field for this kind of quantities, which has the value that is canonicalized to the base unit of the quantity in Newcomb. So then you can kind of use this value to perform, let's say, robust comparison against the value that we want to. And similarly, you can use the member of UDF to find all the immunizations which are in a custom value set that defines vaccines for COVID-19. And then we can combine everything together with this quite complex SQL query that joins all the tables between themselves. It kind of creates at the end the view that we want. So we want to have something like this, that we have all our factors and some of the patient data that we can use for analytics. And I won't discuss this query further, but I just want to show this possible to do this, because there is arguably a simpler way, and that is to use FHIRPath. So let's try to do the same thing using FHIRPath now. So again, same problem. It's just that now I want to use the FHIRPath rather than SQL. And FHIRPath, I'm not sure if you know, is just a language that is designed to navigate or extract values from FHIR resources, as opposed to just generic query language for relational databases. So again, we create the pathing context. There's the query that we had in SQL just for reference. And now we can, again, create our pathing source, this time reading this from an SQL schema, and then define our view in terms of FHIRPath expressions for each of the columns we want to extract. So we can now extract, we start with the patient resource. We know that we want to get some basic elements such as ID, gender. Then we want to get the first postal code of the address. Then we want to find all the conditions of this patient for each, does it say exist? Okay, yeah, that's essentially subsumed by the SNOMED concept for heart disease. Then we want to find all the conditions that, or if there are any conditions, essentially that are subsumed by the SNOMED concept for chronic kidney disease. Then you can see the on observations of BMI that are more over 30, and this time FHIRPath actually provides the unit-aware comparison. So you don't need to worry about the value, the quantity of the actual quantity. And then you can also use the member of telemetry function to identify all the vaccinations and ask the patient if vaccinated with a COVID-19 disease. And that's pretty much it. I mean, this extract operation, which is the pathing operation as well, also allows us to define filters. So we can essentially narrow down the set of patients that we want to export if that's necessary. And at the end, we're getting the same thing. So whether you use SQL or use pathing and FHIRPath, we are getting the same view that defines the properties we want to extract from FHIR of our use case. But arguably, this is a bit simpler. So now, with this knowledge, we can go to our pipeline again, implement step 3. We go to our repository, to our ETL. And what we want to do is essentially take data from the FHIR schema and then create this view and then load it to an SQL schema. So that's what we're doing here. So again, we pretty much use the same code. So we create the FHIR data source. On the input schema, we create the view to extract the one that we want, the data that we want to do, and then we use Spark save as table function to save the view into destination schema in data lake again. And this is just for the purpose of the presentation. I'm using data lake both as the FHIR and the SQL database, but it would be possible to write it to SQL database using Spark JDBC connector, or otherwise you can always save it as CSV files and then load it back to an SQL database later from the same extract. So that essentially concludes part 3 of the pipeline. Now we have our data in this SQL database, and we can as well kind of try to navigate to the database here and have a look that we have this DevDays SQL schema, which has the view, and there are some sample data here for this view. So these are the notebooks, and now we can use some form of orchestration to combine them together into pipeline. And Databricks has a specific thing called workflows. So we can actually go and combine the all these steps and create the actual automated pipeline that runs all these steps in parallel, and then we can run it whenever we want to, or schedule this thing, and it will run and get the data, transform them, and then put it back into data lake. And I'm not going to go how to do this here, but at the repository here is a video that shows how to actually define this if somebody wants to do this in Databricks, because that's type specific. However, what I wanted to show is how we can actually now use this to do analytics. And I will put ahead of data analysis using Power BI and try to actually do something with the data. And fortunately, or very nicely, Databricks provides us with a way to connect directly to Power BI. There is a thing called connector here with Partner Connect. So we can actually go and create a connection file for Power BI and then use it to connect our Power BI to our data in Databricks instance. And we'll have something like this essentially. So we have this connection file, we click on it, we open Power BI. It will connect us to this instance that we've just created, so we can navigate to our specific SQL database. I press the bigger one, but it's okay. We can load the data. We need to change the type of the view to import, so they can add some extra fields to it. And then what we want to do is add this risk score field that will define the risk score for COVID-19. So we have our factors, and now we just want to add a new column that is going to be a customized risk score based on the risk factors. We'll name it a COVID risk score, and then we'll use some formula that essentially is a weighted sum of all different factors to create a risk score. We need to change the type, so they can use different kind of aggregations for this value. And then we can go and do some visualization. So we use the field map. We don't need the filters. We'll now use our postal code as the dimension value. And this already gives us some idea of what's happening here. So we have data for, looks like Massachusetts, United States. Or maybe New York, actually. No. And then we can define the value for the colors to be based on our risk factor. So kind of like aggregate risk score for the whole area. And essentially, this will get us the visualization that we want to create, and we can now add some extra tooltips and then use this to kind of navigate this thing and find areas that are, for example, highly risky with regard of this risk score. Okay, so I think that concludes pretty much part one of the presentation. So that's the pipeline. So now let's look at some of these other things like the recursive data types. So these are things like, for example, item in questionnaire that may itself have other items. And the problem is that the FHIR in principle allows infinite level of nesting, and this can't be presented in SQL schema. So that some choices need to be made. And we made the assumption that very deeply nested questionnaires, for example, are not very common in practice. So we allow the user to select the maximum value of nesting. And this can be selected based on actual data, but it's set globally for the entire data model that we can represent. The other challenge or the other complex topic is the extensions. So they are even more challenging because they are not only recursive data types, but also they can be attached not only to complex, but also to primitive types. And the extension values is a choice of over 50 different types. So even if we kind of limit the number of nesting, representing this in the schema will be very difficult and just create extreme schemas. So the way we use it in Pathling is that we, first of all, the extensions are optional, so we don't need to use them. That's kind of optional feature. And the other one is we chose to create for each of the elements a unique ID, a field ID, and then store all the extensions in a single map column that then we can use to attach extension to simple and complex types. And because extensions are also complex type, they also have field ID, so we can attach extensions to extensions essentially with infinite nesting. Okay, so let's look at some code that demonstrates how to actually use this. So for extensions, we have, again, some data from synthetic data from this smart health IT dataset, and there are some extensions attached to the patient resource, like address, and there are some extensions which are complex one or nested one attached to an address element. And as I said, support for extension is optional, so to enable extension, partly we need to use this parameter. And then the easiest way to get the extensions out is to use the FHIRPath, because it has the extension function, which allows us to just get the value of the extension with a specified URL. And we can both get the extensions from the patient, or also we can get extension on the address element and then unnest the nested extension using this function. And then essentially we can create the view that we want to. And there's also kind of hides the complexity that we use to represent the extensions in the schema. You can just use the FHIRPath to extract the extensions and their values. You can also do it in SQL, but it's a bit more complex, but it is possible. So it's just to show that it is possible to use SQL to do the same thing as well. And now we can go to questionnaires. And I've downloaded some questionnaires that are part of the FHIR specification examples, and they're in this data. And again, the first thing that we can try to do is try to see what the structured questionnaire is that we have. And if you use FHIRPath, you can essentially just use the FHIRPath unnesting to kind of navigate deeper and deeper into the structure. And we can see that we can have some questionnaires, and some of them have only one level of nesting. So let's say this one, some of them are nested in 2 levels, and this one is nested into 4 levels. So if you use 5 as our deepest nesting, we should be able to present our questionnaire and responses in our schema. And maybe more interesting thing is how we actually can extract some values. So if you wanted to get answers and use them as our data in our risk-setting view, you can use, again, expressions for FHIRPath and find the items with specific IDs, and then find the answers and get them out in our use case centric view or in our tabular view. And again, it's possible to do the same thing again in SQL, but it's a little bit more complex. It involves using things like export outer and pivot. But in principle, it's possible to do this. And if you want to, you can look at the code, and it's there. Okay, so that essentially is all about the code. I just wanted to explain a bit more about extract operation. So essentially what it does is allows us to create tabular views on FHIR data using defining the columns of FHIR expressions and using FHIRPath to filter resources and put it in the view. And I guess the most important feature of this is the way it combines the columns into rows. And it does it in a smart way. It means that it only produces combinations that exist in the FHIR data. So for example, here we want to extract name.given and name.family. We're going to produce combinations of Benjamin Franklin and Silence Dogood, which exist in the input data right here, and not the Cartesian product of all the values that exist in the data set. So it kind of does this in a way that produces correct results in the tabular view. So yes, we learned how to use Apache Spark and Pathling to encode FHIR into Delta lakes, pretty much, how to use FHIRPath and SQL to transform complex FHIR schemas into simpler tabular views, and also how to combine this with FHIR bulk export to create an automated pipeline that can be used for FHIR-based analytics. These are my contact details for the conference, and we have the GitHub case, and there's a few rated sessions that are talking about the FHIR bulk export. If you are interested in this one, there's one about SQL and FHIR, and there is one about FHIRPath, and there's also a few sessions about, I think, analytics pipeline, and they have analytics or AI in the title, so it should be easy to identify, that represent, I think, alternative approaches to the same problem. And I think that's it.
Thank you, Piotr. Do we have any questions? We'll start with questions in the room, and then if there's time, we'll get to the Q&A and Hufa.
Hi, I was wondering how fast it is. If you have like millions of records, millions of patients, millions of more than millions of conditions, how fast would it take to load this from the FHIR server to having everything unwrapped?
The answer is I don't have an answer. The answer I can give is that it is in principle is based on Apache Spark, so it's scalable horizontally, and at least the pipeline that does the processing should be able to scale on big clusters, and this should allow us to address this kind of problems.
Hi, I have a question about how you go about questionnaire responses when there are repeating answers, because like in the flattening, I only saw like just the dot notation, just one question is one column, and if you have repeated questions of repeating answers, how does that work then?
As if having multiple responses for the same item?
Yeah.
Well, then probably there's a few choices, and one of them is okay. So one answer is that FHIRPath has syntax for addressing certain elements, so we can potentially get this and address them one by one. More specifically, we can also export them just as arrays and kind of get later SQL to transform in different views. But I guess I'm not too sure exactly how this could be done at the moment. We can discuss this later. But I think that would be my question: what FHIRPath allows in terms of extracting information from the data.
Hi, thanks for the presentation. So actually, one of the things that I wanted to advertise here tomorrow morning, I have a session which is very similar actually to this one, and that's transforming FHIR data for horizontally scalable analytics. Now the question, so with that background, so one of the challenges that we had was when we extract data from a FHIR server, and I saw that you're using bulk export, which is very interesting. The question is, how was the performance of that, and what was the FHIR source that you used? Because I think we tried it, for example, with Happy. There were some performance challenges with it. And also, how do you do updates? So when there are some, let's say I do my analytics today, and then next week I want to update my results. So do I need to extract everything from scratch, or there is an update function? Yeah, thanks.
Okay, so I'm not sure if I can answer the first questions, because I think we didn't actually run a large-scale bulk export tests in this pipeline, assuming that this is going to be addressed by the bulk export implementation. For the second bit, though, this pipeline, I mean, the one that I presented doesn't have it implemented, but in principle, we can use the scenes parameter in bulk export to just export the incremental updates and then merge them back into the data lake. And the data lake merge operation has the ability to update resources based on resource IDs. So if the resource already exists in the data lake with the same resource ID, they will be updated and new will be created. So this way, we can only update incremental updates since the last time they actually run the pipeline, and keep the replica updated in the data lake.
Any other questions in the room? Just want to make sure I didn't miss anybody. Okay. We have a few questions in Hoover, so I'll take a look at those. How often do you refresh the SQL database?
Well, I guess it depends on the actual use case scenario, and this was meant more of as a demonstration of the principles, not so much the production pipeline, but we can probably schedule this daily and nightly if that's the frequency that is needed for data analysts. And I think in this scenario, well, I don't know what would be the required refresh rate, but it can be run as frequently, I guess, as needed, provided that it doesn't that it finishes in time. But yeah, that's the answer. So I guess it depends on the use case, really.
There's another question. When you do refresh, do you completely refresh the data or try to find the changes and only update those?
Okay, so this is related a little bit to, I guess, the question from, I'm not sure what the name is, but yeah, so in this scenario, I mean, we incremental update the FHIR type because they're bigger, and then we actually do refresh everything in this scenario in this use case centric view because it's probably going to be much smaller. So this was the principle here, that the data are merged to data lake and then overall kind of loads entirely into the SQL database. Delta Lake, as such, has the ability to create streaming events for updates. So it is really actually possible, probably, to create this implementation that will be using to streaming to create online view on the data, but that's beyond scope of this presentation. I think there's some challenges to address to actually do this. So at the moment, the answer is incrementally for the replica and then everything for the view in the SQL database.
Another question, how do you handle repeating elements? I'm not sure if you had addressed that.
So I think so I guess that depends again on the context a little bit. So the way I handle the repeated element here is that I was, for example, looking for existence of something. So trying to aggregate them and ask exactly what is that we want to get. Do we actually want all the elements? And then we can get them in form of a list maybe and just kind of combine them in the list field, or do we just want to ask something about all these elements, the list, and kind of answer the question, maybe does the list itself have certain properties? Because I mean, at the end, what we want to get is the tabular view, right? So we need a bit to decide what we actually want to do with these elements, and it has a certain structure. So we can't just freely unnest the list and say just create the fields as is. So you can either ask for specific things and say give me element 1, 2, 3, 4 and put them into columns, or we need to ask, okay, add them together or create a list out of them and put them into the field. That this should be possible with FHIRPath.
I think we have time for just one more from Uva. When you export the FHIR resources in DJSON format, do you export all the versions? How do you handle if you want to show the trending of some resource?
Sorry?
How do you handle it if you want to show the trending of some resource?
Again, I think that this is a little bit the question of how do you want to use bulk or export API. And for this specific use case, we're just getting the most recent version of the resource. And if the version change, then we will update the resource in the replica. But I don't think we, at least in this implementation, have a way to kind of keep multiple resources and see differences between them. That was not the purpose of this pipeline.
All right, thank you. I think that is all for today. We just ask that you use the QR code to fill out a feedback survey for us. All right, thank you.
Thank you.